All right, so we're moving over Firestarter 31. Now remember, I'm telling you certain things are true in this to start, so make sure you're paying attention to that. So the first thing I'm telling you is that line L right here. That's this guy right here. And line M, that's this guy right here. They're parallel. That's what those symbols mean right there. They mean parallel. All right. I'm telling you line N is a transversal. I don't actually need to tell you that because you can see it's cutting through. All right. But that gives us some information. Now, there's 3 different congruence statements, and the reason I could actually give you 4 different types of congruency statements here. But I only asked for 3. The first set of congruency statements that you can talk about are vertical angles. So the reason is going to be vertical angles are congruent. Alright, so for all the next set of stuff, it's because vertical angles are congruent. If you see right here, angle 2 right here is across from angle 3. They're across from each other. Those are vertical angles. 1 is across from 4. They're vertical angles. 5 is across from 8. 7 is across from 6. So those sets are congruent. So I get to say angle 1 is congruent. Remember, I'm using the congruency symbol, not the equal sign. This means angle 4. I get to say angle 2 is congruent to angle 3. I get to say angle 5 is congruent to angle 8. And angle 7 is congruent to angle 6. Now remember, I do not need 2 parallel lines. I don't know if you guys remember that symbol. 2 parallel lines cut by a transversal. Alright? This vertical angles are true no matter what. Alright? Keyword is going to be case. Keyword is going to be case. 2. The second reason that I could have for angles being congruent is I could have a thing called corresponding angles. Now normally I give the angle congruencies first, but I figured it'd be nice to talk about the reason first. Now remember, if you're talking about corresponding angles are congruent, you must have 2 parallel lines cut by a transversal. Alright? So if I look here, 2 is the top left. So this is like a set of 4. And like look, it's the same setup. There's 1, 2, 3, 4, 5, 6, 7, 8. 2 is in the top left, 5 is in the top left, so they correspond with each other. They're in the same spot, just like I slid it over. Alright? So corresponding angles would be the same location. So angle 2, they're both in reference to a new point. So angle 2 is congruent to angle 5 because they're both top left angles. And that's just in reference to this center point. Angle 1 would be corresponding with angle 7 because they're both bottom left. Angle 4 is congruent to angle 6. And then angle 7 is congruent to angle 8. Alright? So that's the second thing. The third thing I could talk about, the third reason, and this is something we've discussed before, alternate interior angles are congruent. Once again, you must have 2 parallel lines cut by a transversal. So I look on the inside of the 2 parallel lines. So this would be the inside. So all this stuff on the inside, that would be the interior. Alright. Now, 4 is inside. 5 is on the same side, so 7 is the interior alternate. So I'm going to put angle 4 is congruent to angle 7. And at the same time, I could say angle 3 is congruent to angle 5. Alright. So another thing I can do, so the last reason would be alternate exterior angles are congruent. And once again, guys, I have to have the two parallel lines cut by transversal. So this has to have that. So these are outside the parallel lines. You see the purple shaded region? Those are exterior, right? So that's exterior, exterior, right? 2 is on the exterior, alternately, so on the opposite side of the transversal is 8. So I could say angle 2 is congruent to angle 8. And then 1, it would be congruent to angle 6. Alright, that's good for the first one. Alright, so Sohcahtoa, what is it used for? The first thing you should be thinking about is right triangles. So right triangles. It's a way to remember the ratio. So you also it's used to recall ratio of sides of a right triangle. Another thing that shows up whenever we talk about is this thing called theta. So it looks like that. It's kind of like an O with it's kind of like a 0 with a line through it. It's a variable, actually. It's called theta. It's kind of like x, but they use it a lot in trigonometry and geometry and stuff like that. So that's called theta. It's a variable. So remember, so is talking about sine of theta. All right, and that's whichever that theta can change. It could be A, B, or C based on this one. Now what we're going to find out is that B is not very possible because B is the right angle. So unlikely it's going to be A or C, not B in this problem, but it could be B in another problem where maybe C is the right angle. So the O part, the OH, stands for opposite on top and hypotenuse on bottom. All right, so that's important. And then we have the Sohcahtoa, right? So the cosine, so that's supposed to hopefully remember that cosine of theta is the adjacent, and adjacent means right next to it, over the hypotenuse. All right, and then toa is about the tangent. All right, so toa is regarding the tangent. So tangent of theta would be your opposite over adjacent. All right, so that's what we're going to do in 3. All right, so number 3 says find sine of A. So that means we're going to use this for theta. All right, so for sine of A, so sine of A, that means my theta is the A part. So this, if A is your theta, if we're referring to A, this is the opposite. Now, the good news is that won't ever change. You never have to worry about messing up the hypotenuse because it's always the longest side. So it's going to be 24 over 26, which is the same thing as 12 over 13, which is the same thing as about I'm going to make that about 0.923. So that's the ratio for the sine, right? What we can do with this later is if we know the side, we know the side lengths and the ratio, we actually use that to find the angle measurements without measuring it. So you can use some algebra properties and trigonometric properties to do that. So now I'm going to do cosine. So cosine. Now I'm actually going to change this to A. So I'm actually going to make this A because I was trying to see if you guys find anybody would notice that it's B cannot be theta because it's the right angle. It just kind of makes things almost really difficult and not very possible. So we're going to change cosine to cosine of A. So if you figured out that cosine of B was not very feasible because it's the right angle, well then you're pretty good. That's pretty good. All right. So so cosine, and now we're going to go to A. So I'm going to change A to my. So I'm going to make it A. So remember, it's going to be adjacent. So adjacent would be the side right next to it, not the hypotenuse. It can't be the hypotenuse ever. So the adjacent over the hypotenuse. So it's going to be 10 over 2.4. All right, I don't know why I put 2.4. 10 over the hypotenuse is 26. So that's the hypotenuse. So 10 over 26 is 0.38. It's about 0.385. Alright? Alright, and so we're going to finish this up real quickly with tangent of C. So that means C is our theta now. Alright? So the opposite would be the 10. And the adjacent, remember it can't be the hypotenuse, so the adjacent is the 24. So 10 over 24, that's going to be 0.417. So it's going to be about 0.417. That's it.